Welcome to This Explainer. Today, we're unpacking the complex physics of a single, everyday four-letter word, Coke. We hear this word all the time, right? But the actual engineering required to produce it, depending entirely on which version you mean, is absolutely mind-blowing. Let's get right into it.
So, what exactly is Coke? Are we talking about the rock-hard, solid carbon matrix that fuels those massive blast furnaces to create the steel building our modern world? Or are we talking about the effervescent, sugary beverage that's probably chilling in your fridge right now? It turns out, this one little word represents two completely distinct pillars of the global economy. And surprisingly, both of these vastly different products rely on some highly sophisticated process engineering. Whether it's forging metallurgical carbon in just extreme heat to reduce iron ore, or chilling a world-famous soft drink for maximum gas solubility, both of them rely on strict mass balance calculations, precise temperature control, and honestly a heroic journey of matter just to reach their final forms.
Section 1. Forging metallurgical coke, the crucible of carbon.
You see, producers can't use just any old rock they pull out of the ground to make this highly purified carbon product. No, they require specific, high-rank, bituminous coal. Think about these strict chemical parameters. They need an ash content strictly below 10% and a sulfur content below 1%. Why? Well, that prevents brittle steel and excess pollution. The volatile matter has to sit perfectly in that 20 to 30% sweet spot. Lower-rank coals, like lignite, they just have way too much moisture. And on the flip side, hard anthracite lacks the thermoplastic bonding properties they need. So, yeah, it's an incredibly strict recipe.
Okay, so once this perfect coal blend is finally ready, it gets loaded into these massive refractory silica brick ovens. And here, the coal is subjected to blistering temperatures exceeding 1100 degrees Celsius. But here is the kicker. This all happens in a vacuum, a completely oxygen-free environment. Because without oxygen, the coal literally can't just burn to ash. Instead, it undergoes something much more transformative.
Section 2. Pyrolysis and thermodynamics. The phase shift.
What's truly fascinating here is how the coal behaves as the intense heat penetrates it. The coal right up against those 1100-degree walls absorbs the energy, triggering a thermoplastic phase transition. It actually enters this melting plastic state between 350 and 450 degrees Celsius. It becomes this thick, swelling mass. And as it melts, it violently releases all those volatile gases, literally pushing them out. Finally, once those gases escape, the remaining pure carbon resolidifies into a rock-hard, highly porous skeleton. So it essentially shapeshifts, right, from a solid to a boiling plastic paste, and then all the way back to a hyperdense solid. Now, engineers generally use two distinct technologies to manage the sheer, incredible amount of gas expelled during that plastic phase. On one hand, you've got byproduct ovens. These operate under a slight positive pressure to capture gases, things like methane and hydrogen sulfide, for chemical refining later. Conversely, non-recovery ovens use negative pressure, basically suction, pulling in a controlled amount of air to intentionally burn off those gases right there in the oven. And the beauty of these non-recovery ovens? The waste heat from that combustion is captured to generate massive amounts of electricity. Finally, after maybe 12 to 24 hours of baking, this glowing, red-hot carbon skeleton is physically pushed out of the oven in less than a minute. And it absolutely must be rapidly cooled, or quenched, before the open air turns all that hard work into a literal pile of ash. Now, historically, engineers used conventional wet quenching, just blasting it with over 1,100 liters of water per ton, creating this massive cloud of steam. But modern facilities, they use coke dry quenching. They circulate inert nitrogen gas over the hot coke, absorbing the heat to produce high-pressure steam and electricity. It's just a brilliant way to recycle that thermal energy.
Section 3. Carbonating the beverage, a shift in physics.
Pivoting wildly here from the blistering heat of the blast furnace to near-freezing fluid dynamics, we encounter carbonation. The absolutely crucial point here is understanding the stark contrast in the physics at play. While metallurgical coke relies on intense heat to drive volatile gases out of a solid mass, beverage coke relies entirely on freezing temperatures and high pressure to force gas into a liquid. It is, quite literally, the exact opposite physical mechanism.
This highly automated liquid journey relies on a very exact recipe: 85 to 90% highly purified water, 8 to 12% of that concentrated famous secret syrup, and precisely 0.5% phosphoric acid to give it that signature bite. And because water makes up the vast majority of the drink, it has to be chemically standardized globally. That way, a Coke tastes the exact same everywhere in the world, even before that super strict 1:5 ratio of secret syrup to water is blended in.
So to achieve that perfect signature fizz we all know, we have to manipulate gas solubility. The blended liquid is aggressively chilled to somewhere between 0 and 4 degrees Celsius. Why so cold? Well, because cold liquids absorb gases much better than warm ones. Then, food-grade carbon dioxide is injected under really high pressure. We're talking between 60 and 80 psi, all while the liquid is continuously agitated. They just hold it there until it reaches a saturation equilibrium of 2.5 to 3.5 volumes of CO2. That right there is the exact mathematical sweet spot for the perfect physical bite on your tongue.
Section 4. Pressure and packaging. Trapping the fizz. Think about it. If you just poured this highly carbonated liquid into a bottle at normal atmospheric pressure, all that trapped CO2 would instantly and violently escape as foam. Messy, right? To prevent this, factories use these massive, automated rotary counter-pressure filling machines. Before a single drop of liquid even enters, these machines inject the empty container with CO2, pre-pressurizing it to perfectly match the high pressure of the liquid waiting in the filling tank.
Because those pressures are now equalized, the ice-cold liquid can gently slide right down the inside walls of the container without foaming up, but the clock is absolutely ticking. Once filled, the container is hermetically sealed within just 1 to 2 seconds to trap the physics of the fizz. PET plastic bottles get tightly torqued tamper-proof screw caps, and aluminum cans get a pressure-locked double-seamed top. If that capping process is delayed even slightly, the gas escapes and the entire product is ruined.
Section 5. A Tale of Two Cokes, the Grand Finale.
What is truly incredible about this whole duality is how it illustrates the sheer spectrum of human ingenuity side by side. You have two vastly different products. One is built on extreme thermodynamics, heating coal to 1100 degrees Celsius to trigger a solid-state phase change that literally supports our skyscrapers and our bridges. The other, well, it's built on freezing temperatures, aqueous chemistry, and high-pressure gas solubility just to create an everyday refreshment. And yet both represent the absolute pinnacle of their respective process engineering fields.
So the next time you crack open a cold Coke while, say, driving over a massive steel suspension bridge, take just a second to appreciate the mastery of thermal and fluid dynamics making both of those things possible. It really leaves us to wonder, what other staggering laws of physics are hiding right in plain sight behind the simplest words we use every single day? Thanks for joining me for this explainer, and I'll catch you in the next one.